Welcome to this lecture on Solution to Exercise 5.3, Question 9 to Question 14 from the book Bartle and Sherbert.
Welcome everyone to this lecture series. Today we are going to solve exercise for section 5.3 from the book Introduction to Ray Analysis by Bartle and Sherbert. So in our last lecture, the part 1 of this video, we have solved question number 1 to 8. So in this video we will solve question number 9 to 19. So let us start with the question number 9. So this is the question number 9. So we are given the function fx, which is equal to x minus 1 into x minus 2 into x minus 3 into x minus 4 into x minus 5. So it has 5 roots, 1 2 3 4 5, and the interval 0 to 7. Now what we are asked is that if the bisection method is applied on this interval, which of the roots is located. So we have to tell that which one of these roots will be located using bisection method. And the same question for gx equal to this on the interval 0 to 7. So let us start with the part A. Now the fx is equal to x minus 1, x minus 2, x minus 3, x minus 4 and x minus 5. So we have to apply the bisection method. So let us make it stables. So in bisection method we have following, we have n, then we have an, then we have bn, then we have pn, the midpoint of an and bn, then we have the value of the function at pn. Sign, in fact we just need its sign, we don't need the exact value. Sign, and then we have the error. So this, in this case we don't need it, but sometimes this is also needed. So these are the things that we use in bisection method. So we use n, an, bn, pn, f of pn, sign, and this, and we use the initial iteration that a1 should be this equal to 0 and b1 is equal to 7, and pn is the midpoint of an and bn. Pn is the midpoint and error is 1 by half of bn minus an. So this is the error, but this we don't need in this case. Right now we don't need it, so we can exclude this because there is nothing, we are not asked about anything about error. So now let us represent all this on a number line so that we can verify the sign at any point. Okay, so let me just put it here, or what we can do is we can get this a little below so that we can have our number line also. Okay, so let me just draw the number line on which I will represent these points. So these are the points. So now let me just put, so this is our 0 7, now 1 2 3 4 and 5. So 1 2 3 4 5. Okay, so now we will verify its sign using this. Okay, so now when n is equal to 1, so a1 is your 0, bn is b1 is 7, and then pn will be the midpoint of this, which is 3.5, and the sign of 3.5 you can, because 3.5 lies here, so this, this will be positive at this bracket will be, this will be positive, this will be positive, this will be positive. So 3 positives and 2 negatives, because x is smaller than 4, in fact x is 3.5, so this negative, this negative, so 3 positive, 2 negatives, so overall this will be positive. Now sign of, because what is the sign of a1? If you look at this, a1 is negative, 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 so all are 5 negatives, so this is negative, this one is positive 7, because all are positive, so this one is positive, this one is negative. So this one is positive, this one is negative. So whenever pn will come out to be positive, then our an will change, and whenever the sign of f of pn will come out to be negative, then bn will change. sorry, this one is negative, this one is positive. So whenever the sign of f of Pn will come out to be positive, then our Bn will change, and whenever the sign of f of Pn will come out to be negative, then our An will change. So in this case, because it is coming out to be positive, so our Bn will change. So this will be same 0, and this will become 3.5. So A2 is your 0, B2 is 3.5. Then f of Pn will be half of this, so which is 1.75. Yes, 1.75. And if you look at this sign, so now if you come here, so positive, negative, 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 negative. So 4 negatives. So again this is a positive. So this is positive. So now your at third step your An will be 0 and your Bn will be 1.75. And now if you look at this, because we have excluded all the, so now we have our A2, A3 is this, A3 is somewhere here, A and B3 is somewhere here. Now because root will lie on in this interval, by bisection method we know that root will lie in this interval, and there is only one root in this interval, which is x equal to 1. So we by bisection method, if bisection is a method is applied, then the root x equal to 1 will be located. We don't need to proceed any further because now we have excluded all the roots. If you look at this, so all these 2, 3, 4 and 5 are excluded in this interval a and b and a3, b3. So here, if the bisection method is applied, since the interval a3, b3, which is equal to 0, 1.75, contains exactly one root of the given polynomial, of the given function, in fact of the given function f. So if the hence if the bisection method is applied, to f, then to f on 0, 7, interval is also important, on 0, 7, then the root x equal to 1 is located. So you will be able to locate x equal to 1 if you will apply the bisection method on the interval 0 to 7. Now let us take this b part. Again we are given this function gx equal to x minus 2, x minus 3, x minus 4, x minus 5, x minus 6. So 9th b part, gx is equal to x minus 2, x minus 3, x minus 4, x minus 5, x minus 6 on 0 to 7. Now g of 0 is, because negative, 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 5 negative, so this is negative, and g of 7 all are positive, so opposite signs on the endpoints. Now let us, so bisection method, if you will apply bisection method, so you need following table, you will make following table. So n denotes the number of steps, an, bn, pn, midpoint of this, and g of pn. So n, when n is equal to 1, your an is 0, this is 7, this is 3.5. Now if you look at 3.5, so positive, positive, then 3 negative, so this is negative, sign of this is negative, sign of this is positive. Okay, so this one is negative, this one is positive. Now n is equal to 1, so this one is 0, 7, then 3.5, and it was coming out to be negative. So because it is coming out to be negative and sign of this is negative, so our this is an will change. So now an will become 3.5. So at second step our an is 3.5, this is 7, and so what will be this? So 10.5 by 2, it is 5.25. 5.25. Now let us look at its sign. So 5.25, positive, positive, positive. So 3 positives, again 4 positive and 1 negative. So on 4 positive, 1 negative, so overall negative. So again because it is negative, so this this will change, so it will come out to be 5 points. So again an will change because sign negative negative, so this will be 7, and now 7 plus 5 12, 12.25. So 12.25 divided by 2, so you will get something like, so you will get 6.125. Yes, so 6.125. Now if you look at this, positive positive, all are positive, so this will be positive. So your this interval will change. In fact, we could have concluded from here because there is only one root at this step, so we don't need to find these values because the interval at the third step 5.25 and 7, this contains only one root, which is 6. So we can conclude from here, directly from here. So again, at third step, the interval A3B3, which is equal to 5.25 and 7, contains exactly one root of gx, which is x equal to 6. Hence, if the bisection method is applied, to gx on 0 to 7, then the root x equal to 6 will be located. So is it, so this is, so we are done with question number 9. Now let us move to question number 10. So let's see what's there in question number 10. Okay, so in question number 10 we are given that if the bisection method is used on an interval of length 1, so the interval of length 1, to find Pn with error Pn minus c less than 10 to the power minus 5, determine the least value of n that will ensure this accuracy. So basically what we have to show, we have to prove that the error at the nth step should, so we want our error to be less than equal to strictly less than 10 to the power minus 5. So we want the error at nth step to be less than 10 to the power minus 5. Now we know that the error in the bisection method at nth step is given by 1 by 2 times bn minus an. So thus we want the least possible n such that this 1 by 2 times bn minus an should be less than 10 to the power minus 5. So we want something like, we want this condition to be satisfied for some the least possible n. Now 1 by 2 to the power bn minus an is nothing but 1 by 2 to the power b minus a, the length of the interval, 1 by 2n minus 1 by 2 times 1 by 2n minus 1 b minus a, this to be less than epsilon. So length of the interval uh, is b minus a. B minus a is the length of the interval, and bn minus an is nothing but 1 by 2 to the power n minus 1 b minus a. So this, we want this to be less than 10 to the power minus 5. So this implies we want, because now we are given the length of the interval is given to be 1, so we want this to be less than 10 to the power minus 5. We want this because we are given that the length of the interval that we are considering is 1. Length of the interval under consideration is 1, so we want this. Now so we want this 1 by 2n should be less than this, so this implies we want 2n we want n such that 2n is greater than 10 to the power 5. We have just reciprocated it, so inequality will reverse. So this is 10 to the power 5. So we want 2 n, least possible n, such that 2 to the power n is greater than 10 to the power 5. Now because log function is increasing function, so we can we can take the log on both sides. So this will imply that n log 2 is greater than 5 log 10. Now because so we can take log with base 10, so then this will become 1. So this implies n is greater than 5 log 2. So we want n, least possible n, such that n is greater than 5 by log 2. So we want n to be this. Now 5 log 2 is, this is equal to, approximately equal to 5 by 0. Because log 2 with base 10, the value of log 2 with base 10 is approximately 0.301. So this will be approximately yours, because when you will divide by 3, so this will be approximately 16.6 something. Okay, so we want an integer, the least possible integer, which is greater than 16.6. So that is, n equal to 17 is the least possible natural number, uh, such that the Pn minus c is less than 10 to the power minus 5 over 1 by 2. So this n equal to 7 is the least possible natural number, such that Pn minus c is less than 10 to the power minus 5. So this is the desired value, n equal to 17 is the desired answer. So we have completed question number 10. Now let us move to the question number 11. So question number 11 basically provides the alternative proof for location of roots theorem. So location of roots theorem we have proved using bisection method, but this also provides a proof for location of roots theorem. So we are given a function f which is continuous on I, and we assume that f of a is less than 0 and f of b is greater than 0. So basically the function is changing its sign from negative to positive on the interval a to b, and we have taken this set w which is equal to x belonging to I, such that f x is less than 0. And then so we have collected all the points in the interval I at which the value of the function is negative. Then and we take w equal to supremum of w, because this set is non-empty, because our a belongs to this set, and also this set is bounded because this is a subset of I and I is bounded. So w is a bounded subset of R, and every bounded subset of R has a supremum, so we can take this w to be supremum of w. So now we have to prove that f of w is equal to 0. So that is, this is the desired point at which the value of the function has a real root. So we are given f of a is less than 0, less than f of b. Second, w is equal to supremum of w, where w is the set of all points in I at which the value of the function is negative. Claim, we have to show f of w is equal to 0. So we will use the infimum property, because w is supremum of w. Since w is equal to supremum of w, so we are going to use the supremum property. So for each n belonging to n, w plus 1 by n, or sorry, w minus 1 by n is not an upper bound. W minus 1 by n is not an upper bound for w. So there exists wn belonging to w such that w minus 1 by n is strictly less than wn, and which is less than equal to w, because w is supremum and w minus 1 by n is smaller than w. So there must exist something in between w minus 1 by n and w. So we are able to find this, and then this implies your this wn converges to w. So this the sequence wn converges to w because it lies between w minus 1 by n to w. So this is converging to w, this is constant, this will converge to w. So this has to, by squeeze theorem, this has to converge to w. So we have generated a sequence outside of we have generated a sequence in w. So wn is a sequence in w that converges to w. So by sequential criteria for continuity, now this w belongs to this I, since wn is a sequence in I and I is closed, so this implies w belongs to I. So this implies f is continuous at w. F is continuous at w since f is continuous on I. So because f is continuous on I, so this f is continuous at w. So by sequential criteria for continuity, the f of wn converges to f of w. So mark it as star. Okay, so f of wn converges to f of w. Now as wn belongs to w for all n belonging to n, so this implies f of wn is strictly less than 0 for all n belonging to n. So this implies limit n tends to infinity, f of wn is less than equal to 0, that is f of w is less than equal to 0. But we have to prove that f of w is equal to 0. So we have to construct a sequence outside of w. We will construct a sequence outside of w for and such that it will converge to w. So we will take a sequence that, so for again for each n belonging to n, consider yn belonging to I such that for each n belonging to n, consider yn belonging to I such that uh, and why we can choose such an I such a yn such that w is less than yn, w is less than yn, and yn is less than w plus 1 by n. Or we can say not, okay, not 1 by 1 by n, we have to, because this might be bounded. Now since f of b is greater than 0 and f of and w belongs to I and b is an endpoint of I, so this implies w is not equal to b. So there are infinitely many real numbers between w and b. So what we will do is we will take this. So let for each n belonging to n, let yn belong to I be such that w is less than yn and this is less than yn, sorry, w plus b minus a w by n, because these two are not equal to 0. So w will be smaller than b because w belongs to I and b is an endpoint of I. So what we have done is, basically if you look at this, so if this is our real line, this is our real line, and this is our a, this is our b, w will be somewhere here which will be smaller than b. So we have taken this distance b minus w, and at each step we are finding this yn which is smaller than this. So we are finding this yn which is smaller than this. So then if you look at this, because by squeeze theorem, because this will converge to w, if you take limit n tends to infinity, then yn will converge to w. So this implies your yn converges to w again, since, and because this yn is greater than w, so this implies f of yn should be positive. F of yn should be positive. So yn converges to w. So by sequential criteria for continuity, f of yn converges to f of w. Now for each n belonging to n, yn is greater than w, so this implies f of yn should be positive, because yn cannot belong to the set w. So this implies yn f of yn is greater than 0, so this implies limit n tends to infinity, f of yn is greater than equal to 0, and this implies f of w is greater than equal to 0. So from star and from a and b, so they mark it as a. From a and b we conclude that, so from a and b we conclude that f of w is equal to 0, hence proved. So from a and b we conclude that f of w is equal to 0. So this completes our question number 11. Now we are going to do question number 12. So let us take the question number 12. So let I equal to 0 to pi by 2, f from I to r be defined by fx equal to supremum of x square cos x. For x belonging to I, show that there exists an absolute minimum point x naught belonging to I. For f on I, also show that x naught is a solution to the equation cos x equal to x square. So what we have to do, we have to do this. There are two parts to it. First we have to show that the function has a minimum, absolute minimum on the interval I. There exists some x naught such that f of x naught is equal to infimum of f over I. And second we have to show that this x naught satisfies this equation. That means cos of x naught is equal to x naught square. So that we have to show. So we are given f equal to supremum of x square cos x on 0 to pi by 2 to show. So we have to show two things. First, there exists x naught belonging to I such that f of x naught is equal to infimum of fi, and second we have to show that cos of x naught is equal to x naught square. So these two things we have to show, that cos of x naught is equal to x naught square and f of x naught is equal to infimum of f of I. So let us prove the first part, that there will exist some x naught. So for that we have to show that the function is continuous, because every continuous function defined on a closed and bounded interval attain its bound by maximum minimum theorem. So we just need to show f is continuous, and if you have known that you have this result, that maximum or supremum of ab is nothing but half of a plus b plus half of modulus of a minus b. So we are going to use this formula here. So from this formula we know that fx is equal to half of x square plus cos x plus half of mod of x square minus cos x. And now because x goes to x square is a continuous function, now since x goes to x square is a continuous function, is continuous on 0 to pi by 2. Also x goes to cos x. All this because this is a polynomial function, continuous everywhere. This is a trigonometric function, continuous everywhere on its domain, and domain of cos x is a whole of R, so it is continuous whole of R. So this is continuous on 0 to pi by 2. So by algebra, and x goes to mod x is continuous on 0 to pi by 2. So by algebra of continuous on R, in fact you can say, because then we don't have to take care of the domain and codomains, range, or and all other things. So by algebra of continuity, we conclude that f is continuous on 0 to pi by 2. Then by maximum minimum theorem, which says that every continuous function defined on a closed and bounded interval attain its bound. So the maximum minimum theorem, there exists x naught belonging to I such that f of x naught is equal to infimum of fi. So we have found some x naught such that f of x naught is equal to infimum of fi. Now we have to prove the second part, that x cos of x naught is equal to x naught square. So that is, we have to show that the function fx equal to supremum of x square cos x, it attains its uh, minimum value at the point x naught. Okay. Now if you look x square, let so now let h equal to x square minus hx equal to x square minus cos x, x square minus cos x on 0 to pi by 2. So then h is continuous on 0 to pi by 2. Also h of 0 is 0 minus 1, which is negative, h of pi by 2, which is pi by 2 whole square minus 0, which is positive. So h of 0 is negative, h of pi by 2 is positive. So by location of roots theorem, there exists c belonging to 0 to pi by 2 such that h of c is equal to 0, that is x c square is equal to cos c. So so we have proved that there exists such a point which in the interval 0 to pi by 2 at which these two are equal. Now we have to show that this c is nothing but this x naught square. So claim is c is equal to x naught, that is this point is nothing but the point x naught. So that we have to show. Now for that, observe that x square is an increasing function on 0 to pi by 2, because it's so this is an increasing function. It is easy to see that this is an increasing function on 0 to pi by 2, while cos x, because it takes values from 1 to 0, is a decreasing function. It's in fact strictly decreasing, you can say. Yeah, is a decreasing function on 0 to pi by 2. So x square is an increasing function and cos x is an decreasing function on the interval 0 to pi by 2. Now for any x belonging to 0 to c, because the c lies between this, so for any x belonging to c, because x square is increasing, so x square is less than c square, while and c square is equal to cos c, and cos c is less than cos x, because cos x is decreasing. So x x less than c implies cos c is less than cos x, and x square is increasing, so x less than c implies cos x square is less than c square, or you can say less than equal to. So this implies f of x is equal to which is equal to supremum of x square cos x is equal to cos x, because cos x is bigger on this interval on 0 to c, which is greater than cos c and which is equal to c square. And now again, for any x in the interval c to pi by 2, because now x is greater than c and x square is increasing on this, so x square is greater than equal to c square, which is equal to cos c, and this is greater than equal to cos x, because cos x is decreasing, so x greater than c implies cos c should be greater than cos x, and x square is increasing, so x greater than c implies x square is greater than equal to c square. So this implies fx is equal to x square, or you can write like this, x supremum of x square cos x, which is equal to x square, which is greater than equal to c square, equal to cos c, or you can say fc. So this is the value of c square, which is equal to fc, and here also you can write it as fc, so that we can compare it with which is equal to f of c. So this, so on 0 c to pi by 2, so this implies fx from both the parts, because here also fx is greater than equal to fc, and here also we have shown that fx is greater than equal to fc. So from a and b, so from a and b we conclude that fx is greater than equal to fc for all x belonging to c 0 to pi by 2. So this implies c is point of c is absolute minimum point, absolute minimum point of f on 0 to pi by 2. Hence, so this implies, because x naught is already a point of absolute minimum point, so this implies c is equal to x naught, that is cos x naught square is equal, cos x naught is equal to x naught square. Hence proved. So we have done this question number 12. So we have shown that x naught is the solution to the equation cos x equal to x square. So now we are going to do question number 13. So again, this is a trickier question. So in question number 13 we are given a solution. So we are given that f from R to R is continuous. Second, we are given that limit x tends to minus infinity f of x is equal to 0. We are also given that limit x tends to infinity f of x equal to 0. We have to prove that, to show f is bounded on R, f is bounded on R, and there and it attains either a maximum or a minimum. And second, f attains either a maximum or a minimum. So basically what we are going to do is we are first going to prove that f is bounded, and then we will show that f attains either a maximum and or minimum. Then we also have to give an example to show that both a maximum and minimum need not be attained. So there may be cases when both of them are attained, there may be case when maximum is attained and not minimum, and there may be case when minimum is attained and not maximum. So we are given that limit x tends to infinity fx equal to 0, and limit x tends to minus infinity also fx equal to 0. So we are going to prove this. So we are going to get a bound for this. So since limit x tends to infinity fx equal to 0 and limit x tends to infinity fx equal to 0, so for epsilon equal to 1 there exists k1 k2 greater than 0 such that fx is less than 1 for all x greater than equal to k1, and fx is less than 1 for all x greater than or less than equal to minus k1 or minus k2. So this is due to this one is due to this, and this one is due to this. Okay, so we are able to find. So then so basically, so we have shown that fx is bounded on the interval k1 to infinity and minus infinity to k2. Now we have to show that it is bounded on the interval k1 to minus k2 to k1. Now, so since f is continuous on minus k2 to k1, so by boundedness theorem, f is bounded on minus k2 to k1, that is there exists m greater than 0, or let us not use m because this is yes, there exists alpha greater than 0 such that fx is less than equal to alpha for all x belonging to minus k2 to k1. So from a, b and c, so let beta equal to maximum of 1 alpha, then from a, b and c we conclude that, so because see here we have shown that fx is less than 1 for all x greater than equal to k1, so that means on the interval k1 to infinity fx is bounded. Here we have shown that on the interval minus infinity to minus k2 the fx is bounded. So we are left with, so if you look at on the number line, then so suppose this is our k1, this is our minus k2. So we have shown that fx is bounded on this, we have shown that fx is bounded on this, and then using this boundedness theorem we have also shown that fx is bounded on this interval. So from all the three, if we will include all three, then we have shown that the function is bounded on the whole of R. So we conclude that fx is less than equal to beta for all x belonging to R, which is equal to, this is because this is nothing but minus infinity to minus k2 union k2 minus k2 to k1 union k1 to infinity. So R is nothing but this, so we are able to prove it. So hence f is bounded on R, at because f is bounded on R, so we can have supremum and infimum. So let m equal to infimum of f of R and capital M equal to supremum of f of R. Now we want to show that one of them is attained, so whichever is non-zero we will prove that that one is attained. So we will do it in two cases. So let us take the two cases. So case 1, okay, so first we observe that, so observe that since limit x tends to infinity fx equal to 0 and limit x tends to minus infinity fx equal to 0. So because the function is approaching to 0 at infinity and minus infinity, so this implies your infimum should be less than equal to 0, because and this should be less than equal to supremum. So 0, so your m is either 0 or it should be positive, and your small m should be either 0 or it should be negative. So now we have two cases. Case 1, when m is not equal to 0. So in this case we will show that this supremum is attained. So for that we assume that, so because m is not equal to 0, so this implies m is greater than 0. So let epsilon, take epsilon equal to, so let epsilon equal to m by 2 greater than 0. Then as limit x tends to infinity fx equal to 0 and limit x tends to minus infinity fx equal to 0 for above epsilon greater than 0, there exists k greater than 0 such that, so we can take k for both the limits, because then if we have different case, then we can take the maximum and the condition will be satisfied for both. So we can have fx minus 0 less than m by 2 for all x greater than equal to k, and fx less than m by 2 for all x less than minus k. So this implies minus m by 2 is less than fx less than m by 2 for all x belonging to minus infinity to minus k union k to infinity. And this implies your supremum of fx, because fx is bounded above by m by 2. So supremum of fx where x belongs to minus infinity to minus k union k to infinity is less than m by 2. Now but because the supremum of f over r is equal to m, which is greater than this, so that supremum must be attained on the interval minus k to k. Let us look at this on the number line. So this is the number line, this is your minus k, this is your k. Now fx is less than m by 2 in this area, and fx is less than m by 2 in this area, but overall you know that the maximum value of fx is m, supremum of fx is m, so that m must be attained in this interval, right, in the interval minus k to k. So this implies m, which is equal to supremum of f over r, must be equal to the supremum of the function f on the interval minus k to k. So the supremum of f over r must be equal to the supremum of f over minus k to k. And what does this implies? Now since f is continuous on minus k to k, so by maximum minimum theorem, there exists x naught or c belonging to minus k to k such that f of c is equal to supremum of f over the interval minus k to k, because every continuous function on a closed and bounded interval attain its bounds. So fc must be equal to this supremum, and this is nothing but your m. So this implies the maximum is attained, maximum of f is attained at c belonging to r. So we have shown that maximum is attained. Now we will show that so there in the case 1, when m is not equal to 0, we have shown that this maximum is attained, m is attained. Now we will show that if m is equal to 0, so case 2, when m is equal to 0. So now we have two possibilities. Sub case 1, when your infimum is also 0. So in this case your function will be a constant function, because supremum is 0, infimum is 0, and fx lies between supremum and infimum, so it has to be 0. So this implies f is equal to 0 for every x in r. Yeah, f is equal to 0 on r, that is f is a constant function. So this implies fx is equal to m is equal to capital M is equal to 0 for every x in R. That is, your supremum and infimum are attained at every point in R. So we just needed to prove one point, but here we are getting that the supremum and infimum is attained at every point of R. So in subcase 1 also the supremum is and infimum is attained. Now subcase 2, sub case 2 when m is not equal to 0, that is m is less than 0. So then what we will do is we will consider the function. So let h equal to minus f, then supremum of h of r will be equal to minus of infimum of f of r, because h is equal to minus of f, so which is equal to minus m, which is greater than 0. So because supremum is greater than 0 and h is continuous, h also limit x tends to infinity hx, which is equal to limit x tends to infinity minus fx, which is equal to 0, and similarly limit x tends to minus infinity hx will be equal to 0. So by case 1, because the supremum is positive and limits are 0, so by case 1 there exists c belonging to r such that h of c is equal to supremum of h over r, which is equal to minus m. So this implies minus of fc is equal to minus m, that is fc is equal to m. So infimum is attained in this case. So hence the minimum is attained in this case. Thus from all the possible cases, we conclude that either maximum or minimum is attained at some point in R. So this proves the part 1 of this question. Now in the next part we are asked to give an example of a function that satisfies these properties, but one at exactly one of either one exactly one of maximum or minimum is attained. So let us look at that example. So question number 13, part B, give an example. So we are going to give an example of a function. So we are let me just copy paste this. Okay, so we are asked to give an example of a function to show that both a maximum and a minimum need not be attained. So for this what we will do, both a maximum and minimum need not be attained. So for this because now if you look at the number line, let us look at our Cartesian function. So what we are given is that the function is approaching to 0 when x approaches to infinity. So x is approaching to minus infinity, and here x is approaching to infinity. So either the function is coming like this or the function will come like this. If it is coming from the negative side, then it will come like this, or the function is it will come like this. Or so we can have the function like this, so we can have some function like this, or we can have some function like this, or what we can have is so anything in between, or you can have something like this going up and down, and then in here so anything like this, or you can also have this like this. So also you can have a function like this. So all such functions will work. So all such functions will work, so all similar type of functions. So basically this is happening. So now we know a very good example of a function which goes like this, which you must be knowing. This is the Gaussian function, which has this cap over the interval. You must have studied that function while doing probability, because it comes in the normal distribution. Very important function which have a graph like this, and that is your, if you look, so that is your e minus x square by 2. So this function on the interval r to r, this function is satisfies this, and it has the maximum value 1. It will attain 1 at some point. So its graph is like this. So it will attain 1, then it will drop, and it will go like this. So this is the 1 0. So maximum value of this function is 1, which is attained at 0. If you put it 0, so One example is this function, the Gaussian function. There are other examples. You can also make one such example. So first is this known function fx equal to e minus x square by 2 on r, then limit x tends to minus infinity, fx is 0, also limit x tends to infinity, fx is equal to 0, and supremum, the function attains m is equal, the function is bounded because the range of this function is from 0 to 1. So infimum of fx is 0, infimum of f over r is 0, supremum of, oh, sorry, infimum of f over r is 0, and supremum of f over r is 1. This is not attained, right? This is not attained, and this is attained at x equal to 0. So one such example is this. So you can have this. So f of 0 is equal to 1, which is equal to m. So this is the this is the function Gaussian function. This is called Gaussian function, and it is used in normal distribution. So this is also called bell curve. Okay, so this is very important function in mathematics, very important function. It has a lot of application, it comes at lot of places. Now another function that we can make is, if you want something which is attaining the infimum, then you can take the negative of this function. So then the graph will come down and you will have infimum will be attained and supremum will not be attained. So in that case supremum will become 0 and infimum will be -1. So you can take the minus. So if you want infimum to be attained, then you can take the negative of this function. Now if you want another function, another example, then you can make one such example. Now there is one more function that has this type of curve, which is, but it goes, if you look at the graph of 1 by x square or 1 by x. So if you consider the graph of 1 by x square, 1 by x square is this, right? So 1 by x square. Also if you look at the graph of 1 by x, then it goes like this and it goes like this. So but they are unbounded around 0, right? Unbounded around 0. So what we can do is we can restrict this function in such a way, so we can remove this part. So what we can do is we can remove this part. So what we can do is we can simply remove, we can restrict our function like this, and from here we can define another function keeping the continuity intact, because we want the function to be continuous. So we can have the continuity intact, and we can we can have lots of function like this. So if I define fx equal to 1 by x square when mod x is greater than 1, and we can define it to be constant function 1 when mod x is less than equal to 1. So basically we are defining, so this we can define like this. So basically we are defining it is equal to x square if x belongs to minus infinity to -1 or 1 to infinity and 1 otherwise, that is on when x belongs to -1 to 1. So now we have removed the point at which the function is gets unbounded, -1 to 1, x belongs to minus, if x belongs to. So now this function, if you look at the graph of this function, how it will be, if you look at the graph of this function, it will be like this. So suppose this is 1, this is, so this is -1, this is 1 0, okay, this is 1. So the function will come like this, the function will go like this. So this is the portion of 1 by x square. Now it is being constant here and continuous also. So then this function, so clearly limit x tends to minus infinity fx equal to 0, limit x tends to infinity fx equal to 0, infimum of m equal to infimum of f over r is equal to 0, and m over supremum of f over r is 1, and if this is attained at f of any point in between this, you can take any point, so it is attained on all the points. So this is in fact f of, you can say 0 also. So this is another example. So you can make one such example. You can also, you could have also gone for this function to like this 2 minus x square. If you could have 2 minus x square, so this, you just have to make sure that the function has the function should be continuous in this domain, it should be bounded, and second thing, it should have the continuity. So that means the limit at x equal to -1 should be equal to 1 in this case, and limit at x equal to 1 should be also equal to 1. So this satisfies that property. So you could have gone for 2 minus x square also. Instead of taking the constant function, you could have gone for this also. So this is all about this. So let us move to the question number 14. So what is the question number 14? In this question, so this is the question number 14. F is a continuous function from R to R. Beta belongs to R. If x naught belongs to R, it says that f x naught is less than beta, then there exists delta neighborhood u of x naught such that fx is less than beta for all x belonging to u. So this is similar to the question where we've proved that if f is continuous at C and fc is greater than 0, then f of x is greater than 0 for all x belonging to some v delta neighborhood of C. So this is this result is similar to this result. So let us try to prove it. So either what we can do is we can use this result also, or we can directly prove it. So now right now, either if you want to use this result, then you can redefine your function h in such a way that the function becomes positive at that point, or you want to use the negative result, and you can use that, but we will directly prove it. So for that, so we are given f continuous on R, second x naught belongs to R such that f of x naught is less than beta. To show there exists some delta greater than 0, to show there exists some delta greater than 0 such that fx is less than beta for all x belonging to delta neighborhood of x naught, which is your u. So what we will do is now we will take epsilon equal to, so let epsilon equal to half of beta minus fx naught. So why we are choosing this epsilon? Because see, if you look at on the number line, because it is easy to see such things on the number line. So if this is your beta, this is your fx naught, okay, so you want some delta. So what you will do is you will take epsilon, you are taking epsilon this, so this is your fx naught plus epsilon, this is your fx naught minus epsilon. And now because f is continuous at x naught, so there will be some delta such that all the points in this will lie in this region. So that's why we have chosen epsilon equal to half of this distance. Half of this distance, epsilon is half of this distance. So for such an epsilon, so now for this epsilon, what, because since limit x, so since f is continuous at x naught, since f is continuous at x naught, so there exists delta greater than 0 such that fx minus fx naught is less than 1 by 2 times beta minus fx naught for all x belonging to v delta neighborhood of x naught. So this implies, now when you will open this, so this implies 1 by 2 times beta minus fx naught is less than fx minus fx naught is less than, so this is minus 1 by 2 times beta minus fx naught for all x belonging to v delta neighborhood of x naught. So now we are going to use this inequality. So using this inequality, what we will get, so this implies fx minus fx naught is less than 1 by 2 times beta minus 1 by 2 times fx naught. for all x belonging to V delta neighborhood of x naught, and this implies fx is less than 1 by 2 times beta plus 1 by 2 times, because this fx naught will come here, 1 by 2 times fx naught for all x belonging to V delta neighborhood of x naught. Now because this fx naught is less than delta, oh sorry, this fx naught is less than beta, so we can replace this by beta since fx naught is less than beta. So this completes our proof of question number 14. We are able to show that fx is less than beta for every x in the delta neighborhood of x naught. So in this video we will solve till here. So we take a break now, and in next video, which is part 3 of this solution to exercise 5.3, we will solve from question number 15 to question number 19. So thank you everyone, and have a nice day. Bye.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.